Johnny here with Simpson Math. In this video, we're going to start talking about the arc length, but really we'll do that in a later video. To calculate the curvature of some function, that the length of an arc over a certain interval, we just simply apply the formula that is written above me. Bam! Just really easy. In fact, you could probably just skip this video altogether and get straight started on the homework. But I hate to just say, hey, here's a formula and go do it. So in this video, my goal is to do my best to show where the arc length formula thing above me comes from, how we come up with it. And to get started, I have a little project for you to work on. I've got two scenarios here. This first one, nice and simple. I could give it to a middle schooler and they could probably play with it. We have this line defined on the x-axis from 1 to 5 and on the y from 3 to 6. And I just want to find that length L. So it's a straight line. I think you can do it. Looks very, Pythagorean to me, like Pythagorean or something. So figure out what L is. Then I think that's going to help you prepare for the second task, which is same situation. We have x1 and x2, y1 and y2, and I'm asked to find an equation that will calculate L, the length of this line segment. So do it with numbers first, pause the video, and see if you can come up with an equation for capital script L. Did you pause the video? Did you try it? I was serious. Pause the video and come up with a point. I'm not going to start talking. All right. Let's see. Here, we teach our students back in the day to visualize a triangle, because then we can use the Pythagorean theorem on right triangles. But let's think about what's going on here. I am finding the difference between 1 and 5. So whatever x values you give me, I want to find their difference. You could count off 4, or you could just say 5 minus 1 is 4. So we find that distance. Similarly, we go off and we find the y difference. The difference between 6 and 3 is 3. And then we can set up a Pythagorean theorem. It says that the L squared will be 4 squared, but I'm not going to call it 4 squared. I'm going to call it 5 minus 1 squared. Plus, and then over here, it's the change in those y values, or the difference in those y values. I'm going to call it 6 minus 3 squared. So L would just be equal to the square root of that stuff. I agree. This is going to be 16 plus 9, that's that 25 we're all familiar with, and we get 5, the Pythag triple. Okay, hopefully though, looking at that, I can now come up with an equation for capital L. I claim capital L squared will give me, or will be equal to, the difference in x values. I could call that x2 minus x1, that's fine. I'm going to get a little bit, I'll do that first. x2 minus x1 squared. Plus the change in those y values, or the difference in those y values. y2 minus y1 squared. That's simply the Pythagorean theorem. Now I keep saying difference or change. Notice I'm changing in these x values. I went from 1 to 5. That's a change of 4. So we have notation for that, the delta symbol. So I'm just going to play around with that. Script L squared. Another way to say this is the change in x squared plus the change in y squared. So then if I want to find L, I just square root both sides. All right. I claim that's a good formula to find out. And I claim that's going to help me with my next thing, where I've got this function here, f, defined over a to b. And I'm just going to assume that f is a continuous function and its derivative is continuous as well. So I'm just going to make sure everything's fine and dandy. And this time I'm not calculating a line segment, the distance. I want to calculate the curvature. So I still want to calculate the length of this curve of f of x over a to b. I want to know, what does that measure? The best way would be to get a string, put the string out here, cut the string, and then measure it on measure. No. I need to come up with a way to talk about the length of that curve. Now, if I just try the Pythagorean theorem here, it doesn't make any much sense. Like, the change in x is the difference between a and b, but the change in y, it doesn't even look like anything's happening. But, yeah, this just doesn't make any sense. Even if I had chosen a different y value for that to end in, that creating a triangle would just be a rough estimate of that length. I think what I'm going to do is I'm going to partition this up. That's kind of been the whole story for the past 2 classes of calculus, where we just start to partition things up. So I'm going to cut this into maybe 5 equal slices. I'll call that x1, x2, x3, and x4. And then I'm going to draw points on the function at those x values. And then I'm going to draw the curve using just those points. So no curvature, just straight lines. So something like that. I'll call that pink stuff L. I want to find, or actually no, just kidding. The L is the length of the black curve. But the pink stuff may be a good estimate. At the start, that nice parabolic looking thing, by cutting up those partitions, we can tell it's not going to be identical, but the length of this straight pink line will be very close to the length of that black curve. And that seems to be very true, at least until I get to this last partition. And even then, it's a close enough estimate. This distance of 1 versus that distance of maybe 1.3 or something. So these pink partitions, they're just estimates of what I'm after, the black curvature of that line. Okay. I can calculate the individual L's. Let's call this one L1. L1 is equal to, and we just mentioned this, the square root of the change in x squared plus the change in y squared. I'm going to call this the change in x squared plus the change in y squared. This comes from what we just talked about. That's the Pythagorean Theorem. Change in the x's, change in the y's. You sum them and square them, you'll get the square of that hypotenuse. And I just want it, so I square root everything. All right. Now, I think what I want to do is, I don't know why I have that in my notes, so I'm just going to skip over it. I do have that though. Now, every line segment will have this same feel to it. So the line at the nth partition, maybe I'm talking about the second one, maybe I'm talking about the fourth one, but it doesn't matter. Whatever partition, it's going to have this same feel to it. I'm just going to square root the change in x and the change in y, those being squared. And then if I wanted to find the total length, I would just sum up all of those lengths. This is capital sigma. It just means sum. We need to sum up some things. We're going to be talking about that symbol a lot in the upcoming lectures. But right now, if you've never seen sigma before, it just means we need to do a lot of summing, add up. So I need to add up all of these L partitions. Right now we have 1, 2, 3, 4, 5 little L's that we need to add up to get an estimation of that total length. This just means I'm going to start at the first partition and I'm going to stop at the nth partition. So in my example, we have 5 partitions, but you know the idea. These partitions will give us a good estimate, but then we're going to want to go through and we're going to want to create more partitions. We're going to want to make these L's even smaller, or these changes in X's even smaller. In fact, we're going to do that over and over again. We're going to create more partitions and more partitions. So these changes in X's get so tiny that they are limiting to 0. That's the whole goal here. So however many partitions you have, you start the first one, you go to the end, you sum up all those lengths, and that'll give you a really good estimate of that curvature of the Earth. Not the Earth. Curvature of that function. Okay, I'm going to factor out that change in X. I just mentioned I'm trying to make those changes in X's very small. I'm going to take that change in X and I'm going to factor it from this, from the radicand. So if I factor it out, it's like anti-distribution or just division. So the change in X squared divided by change in X squared leaves me with 1. And then if I factor that from this, well, that just kind of puts it in the denominator. That should make some sense to you. If this were redistributed, this times 1 is itself, and this times this fraction, those would reduce, leaving me with just the change in the y. So I'm just factoring out that change in X squared. Now, if you have a square root of a product, then you can separate it out. So this is the square root of the change of X squared times the square root of that binomial. And so I need to still multiply by the square root of the change in x squared. What is the square root of something squared? Well, those just kind of undo each other, and I'm left with the change in x. Now, change in x, we've been saying that all through Calculus 2, all through Calculus 1. We have a different notation for the change of x. We call that with respect to x, or dx. I also want to, acknowledge this. If you have something squared divided by something squared, that square can apply to both the numerator and the denominator. So I'm going to create this, I'm going to rewrite this as the change in y over the change in x, all being squared. All right. Now this notation, we've been talking about it, this change in y with respect to x, dy dx. This is just the derivative of y with respect to x. That's all this says. Dy dx. Derivative of y with respect to x. Y in this game is the function f of x. So this is just claiming, or it's telling you to find the derivative of f. Well, I'm going to call that f prime. I'm not sure if that is more interesting. And we mentioned earlier, I'm trying to get that x to go to 0. So I am going to, another way to say that though, not actually that. What I want is more and more partitions. There we go. The more and more partitions I make will make that change in x smaller and smaller. But that's what I really want. I want this n to go out to infinity. I've got an n of 5 here, and it looks like a really good estimation. If I made 10 partitions, it'd be better. If I made 100 partitions, that'd be even better. If I made an infinite number of partitions, then I think I'd have the actual arc length. Oops, left off a square here. Change in x, it's really just a delta x, but right now I'm about to acknowledge that when we limit a sum, this is integration. We're summing up all of those little bitty widths of x, infinite number of them. That's going to give it to me. L is the integral, the sum of all those little pieces from A to B, of the square root of 1 plus f prime of x being squared with respect to x. All right. I'm right with you with what in the world did he just talk about? I was just trying to show you where this arc length formula that I have written above me, where it comes from. So let me walk through that one more time real quick. I got a function, this black curve, f of x. I want to know the length of that curve. Well, one way, a really good way, would just be to partition it. Draw the pink curve in there, and the more partitions, the better. If I just had 2 partitions, I'll call this capital X of 1. Okay, yeah, I could find the length of those 2 line segments. And actually, that would probably be a really good estimate. If I just did one partition, if I just went straight here to here, that's a good estimate too, a distance of 6 or whatever. But it doesn't account for the going up and then going back down. So the blue is an okay estimate. The orange is better. Hopefully you can tell that the pink is even better. And the more partitions, the better. Well, I can calculate the distance of each one of those little partitions. They're just straight line segments. So we can use the Pythagorean Theorem or like a distance formula just to figure out those distances. It's the square root of the change in x squared plus the change in y squared. So then the total length will just be to sum all of those up. If you have 5 partitions or 10 or 100 billion, you just sum them up and you'll have your length. Now, I was doing some fancy footwork here, and you just have to like maybe go with the flow a little bit. But I factor out this change in x to make it look like this, and I acknowledge that anything squared over something else squared, you can rewrite that as the fraction itself being squared. Okay. Then, what did I do? Oh yeah. Then I said, well, this change in y and change in x, that's just what we've been talking about. We haven't used this notation maybe we used it once, like on the first day of calculus, the first week. But since then, we've been using d and like big D's. But it's just talking about change in y over change in x. That is a definition of a derivative. So I'm finding the derivative of y with respect to x, f prime. This change in x, that's just letting us know we're talking about the x variable as it's going along, that dx. And if we sum up all those partitions, and we limit those partitions, making them go out to infinity, so 5 gadillion, 6 gadillion, a bajillion Googles, out to infinity, and here we go. The arc length formula states this. You just integrate from along the interval of 1 plus the derivative of the function squared. Bam. Alright, my next video we will do some examples and show you how easy this is.